Hello friends, I'm Dr. Gaurav. In this video, I will discuss about Carnot Vapour Power Cycle. Contents are Carnot Vapour Power Cycle, performance parameter of Carnot Vapour Power Cycle, impracticalities associated with Carnot Vapour Power Cycle. First is Carnot Vapour Power Cycle. The Carnot cycle is the most efficient cycle operating between two specified temperature limits. The Carnot cycle is an ideal cycle for vapor power plants. It has the maximum thermal efficiency for given temperature limits, and it serves as a standard against which actual power cycles can be compared. However, the Carnot cycle is not a suitable model for power cycles, as there are so many practical difficulties are associated with it. Steam is used as working substance. The Carnot cycle is shown schematically and on a pressure volume, that is PV, temperature entropy TS, and enthalpy entropy diagrams in figure. So this is Carnot Vapour Power Cycle. This is the TS diagram of Carnot Vapour Power Cycle. This is the PV diagram of Carnot Vapour Power Cycle. This is the HS diagram of Carnot Vapour Power Cycle. In Carnot Vapour Power Cycle, there are four main components. First is boiler, second is turbine, third is compressor, third is condenser, fourth is compressor. Now this is the TS diagram. In this, first of all, draw the dome of this TS diagram. This is the dome. Then draw two horizontal lines, this one and this one. Now how to draw the points we will discuss in the later section. For the PV diagram, again draw the dome. This is the dome, and then again draw two horizontal lines, this one and this one. For the HS diagram, again we need to draw the dome. This is the dome. Then draw two pressure lines. First pressure line is this one, draw this line, then draw second line, this one. It is clear from the figure that if at the entry of turbine the condition of steam is wet, then the cycle will be 1 dash, 2 dash, 3, 4, 1. That is, if at the entry of the turbine the condition of the steam is wet, then the cycle drawn will be 1 dash, 2 dash, 3, 4, 1 dash. Now, if at the entry of the turbine the condition is dry saturated steam, then the cycle drawn will be 1, 2, 3, 4, 1. That is 1, 2, 3, 4, 1. This is applicable when at the entry of the turbine, this one, the condition of the steam is dry saturated. All four components associated with the Carnot Vapour Power Cycle, that is compressor, boiler, turbine and condenser, are steady flow devices, and thus all four processes that make up the Carnot Vapour cycle can be analyzed as steady flow processes. The kinetic and potential energy changes of the steam are usually small relative to the work and heat transfer terms, and therefore usually neglected. Then steady flow energy equation per unit mass of steam reduces to this equation: heat in minus heat out plus work in minus work out equal to enthalpy associated with the exit steam minus enthalpy associated with the inlet steam. The Carnot Vapour cycle consists of the following four processes. Below analysis is done by assuming that steam enters the turbine as dry saturated, that is, follow the cycle 1, 2, 3, 4, 1. Now, the first process, process 4.1, represents reversible isothermal heat addition in the boiler, that is, heat addition at constant temperature. Heat is supplied to the feed water, which is saturated water in a boiler. Latent heat is supplied and isothermal evaporation of water takes place at constant pressure until the water gets converted into dry saturated steam. In this process, work in equal to work out is equal to 0 and heat out from the system is also equal to 0. You can see here, this is the first component boiler. Entry point is 4, exit point is 1. In this we are supplying the heat. The condition of the fourth point is such that it is or it represents saturated water condition, that is saturated liquid condition. Now when we supply the heat, then this fourth point will be converted into point 1, that is, it will become dry saturated steam, and the amount of heat supply is known as latent heat of vaporization. So if you apply this condition in this equation, that is W in W out equal to 0, this will be 0, Q out equal to 0, then Q in will be equal to enthalpy associated with exit steam. Exit steam is 0.1 and inlet is 4. So this will be equal to H1 minus H4. So we will have Q in equal to Q1 equal to H1 minus H4. It is also given as Q1 equal to area under the line 4.1 in the TS diagram. So the value of the area, you can see the value of the temperature T1 equal to T1 dash equal to T4 equal to TH, higher temperature, TH is higher temperature, and value of the pressure is P1 equal to P1 dash equal to P4. So if you have to find out the area, then the value will be temperature into change in entropy, because temperature is constant. So we will get this one, T1 ds, T1 into, as we are moving from 4 to 1, then the change in entropy will be S1 minus S4. Small symbol represents per unit mass. So this is the specific entropy. So we can say Q1 equal to T1 S2 minus S3, as S1 equal to S2 and S3 equal to S4. So as we have drawn the line 4.1, in the similar manner we can draw the line 4.1 here and 4.1 in this HS diagram, 4 and 1. Next process is process 1.2, isentropic, that is constant entropy expansion in turbine. So this is turbine, point 1 is entering and point 2 is leaving. Now the steam, that is dry saturated steam, enters the turbine and it will rotate the turbine blade, due to which we will get the work output, and the condition of the steam after rotating the turbine will be 2. So from 1 to 2 there is a expansion process, and we are getting the work output. So in this case Q in Q out equal to 0 and W in is also equal to 0, and we are getting W out only, and in inlet steam is point is 1 and exit steam point is 2. So you can see here this process is isentropic, so we have drawn the vertical line, that is S1 equal to S2. In the same way, this is the nature of constant entropy line 1 to 2, and in HS diagram again we will get a vertical line from 1 to 2. So we are getting the work output, so this will be a positive work. So the turbine work will be equal to, if we apply the condition Q in Q out 0 and W in 0, then we have minus W out is equal to H associated with the exit steam and H associated with the inlet steam. So this will be H2 minus H1. So minus W out is equal to H2 minus H1. So W out will be equal to H1 minus H2. So we will get H1 minus H2. This is the turbine work. Next is process 2-3, reversible isothermal heat rejection in condenser. You can see here third component is condenser. So the point number 2 will enter the condenser and become point number 3. This is the inlet, this is the exit. And what we are doing here, we are taking the heat from this point number 2, which is a wet point. So there will be a heat out from the condenser, and so we will get the point number 3. So in this case Q in equal to 0, W in and W out equal to 0, and this is a constant temperature heat rejection process. So that's why this line will be a horizontal line from 2 to 3. In the same way 2 to 3 here, 3 here, and in the HS diagram 2 to 3 here. So if you apply that condition in this equation, then what we will have? Q in 0, W in 0, W out 0, exit point is 3, H3 minus H2, it will be equal to minus Q out. So Q out will be equal to H2 minus H3. H2 minus H3. It is also given as Q2 equal to area under the line 2, 3 in the TS diagram. So this is the TS diagram, and area under the line 2, 3. 2, 3 will be equal to this TL. TL equal to T3, T2 dash and T2, and the value of the pressure is P2 equal to P2 dash equal to P3. So if you have to find out this area, then the temperature will become the width, and the height will, so temperature is the height and the width will be S2 minus S3, or we can say S3 minus S2. So our formula will become TL ds, change in entropy, TL into S2 minus S3, because S2 is more than S3, so we have taken S2 minus S3. Next is process 3-4, isentropic, that is constant entropy compression in compressor. So here we are having a compressor, entry point is 3, exit point is 4, and we are supplying work into the compressor. So work in. So in this case Q in equal to Q out equal to 0, and W out is also equal to 0. So we are having only W in this case. So what is compression is doing here? Because of this compression work, the point number 3 will become point number 4, and this is isentropic compression. So we will have a vertical line here 3 to 4. This is 3 to 4 isentropic process, and again in the HS diagram we will have a vertical line 3 to 4. So what we can say, if you apply the condition here, then Q in is 0, Q out is 0, W out is 0, and exit point is point number 4, and inlet point is point number 3. So W in is equal to H4 minus H3. So we will have H4 minus H3. So you have seen here we are having only two pressure. First is higher pressure, that is boiler pressure, and second is lower pressure, that is condenser pressure. So we have drawn only two pressure lines. Next is performance parameter of Carnot Vapour power cycle. In this, first is thermal efficiency of Carnot Vapour cycle. Efficiency formula is given as net work done divided by heat supplied. So net work done will be equal to turbine minus compression work divided by heat supplied is Q1. Or we can also define this formula as heat supplied minus heat rejected divided by heat supplied. So we will have Q1 minus Q2 divided by Q1. If you put the value of Q1 and Q2 and Q1, you will get this relation. And cancel the common term, we will get TH minus TL divided by TH. It will be equal to 1 minus TL divided by TH. We have already derived this formula in case of Carnot cycle. This formula can be remembered as 1 minus lower temperature divided by higher temperature. Second formula is for work ratio. Work ratio is defined as net work done divided by turbine work, or we can say turbine minus compressor work divided by turbine work. If you put the value of turbine work, it will be equal to H1 minus H2, and the value of compressor work is H4 minus H3. You will get this relation. A low work ratio implies large compressor work. Large the compressor work, lower the work ratio. Next is steam rate or specific steam consumption. It is defined as the flow rate of steam per unit of power developed, and the unit is kilowatt hour. So steam, or we can say specific steam consumption, is equal to steam flow rate divided by power output. It will be equal to 3600 divided by net work done. It will be equal to 3600 divided by turbine work out minus compressor work in, and then it will be kg per kilowatt hour. So to make this kilowatt hour, what we have done, we have taken the term 3600 because in 1 hour we are having 3600 seconds. Next is heat rate. Thermal efficiency can be expressed as heat rate, which is a measure of the rate of heat input required to produce unit work output in 1 kilowatt. So we will have formula as 3600 multiplied by Q1 divided by net work done, and it will be equal to 3600 divided by efficiency formula, and the unit will be kilojoule per kilowatt hour. Next is impracticalities associated with Carnot Vapour power cycle. The cycle is more difficult to operate in practice with superheated steam due to the necessity of supplying the superheat at constant temperature. So maximum possible temperature is limited. So the meaning of this line is that this is the maximum point you can get in this cycle, point 1. You cannot go beyond this point, that is, this point cannot be superheat point. If you go for superheat point, then the temperature will change, because if you draw the pressure line will be in this way, and the point 1 will be shifted here. If the point 1 will be shifted here, then there will be change in temperature. So it will not make the Carnot cycle. So there is a limitation for point 1. It can be only the dry saturated point. It cannot be superheated point. In the turbine, the dry saturated steam expands isentropically. The quality of steam decreases during expansion. The presence of high moisture contained in steam will lead to erosion and wear of the turbine blades. You can see in the TS diagram, if we have limit the point 1 up to here, then we will get this point here, and at this point the quality of steam, that is dryness fraction, may be less than 0.88. If the value of the dryness stream is less than, if the value of the wet stream is having the value of dryness fraction less than 0.88, then there are chances that there will be erosion of the turbine blades because of the moisture present in the stream. So if we have a point 1 on the right side, then this point 2 will also shift in the right side. Then the dryness fraction for point 1, point 2 will be greater than 0.88. If the value of the dryness fraction is greater than 0.88, then our blade will not erode. So because of this limitation, we will get 0.2 here, and there are chances that there will be erosion of the turbine blade. Third point is, it is difficult to control the condensation at stage 3 before reaching to saturated liquid state. So to obtain 0.4 here, we need to have 0.3 here. So what is 0.3? If we are going from 0.2 to 3, there is condensation. So in the process of condensation, you have to do this process in such a way you get the 0.3 exactly here. Otherwise, you will not get the 0.4 here. If 0.3 is on the left side, then there will be a change in the 0.4, and due to which our process will not be constant temperature process, that is 4:1. So there is a limitation for 0.3, it must be here. So when this point is here, then it is difficult to design such a condenser that will produce the 0.3 exactly here. It is difficult to compress a wet vapor, that is water plus steam, isentropically as required by the process 3-4 because of large specific volume of vapor than liquid. The compressor size and work input will have to be large, and this higher compressor work will reduce the thermal efficiency of the plant. Now I have told you that the 0.3 must be here, that is it will be a wet point. Now the process 3-4, in this we are having isentropic compression, then compressor have to do work in such a way that 0.3 will become 0.4. Now for a compressor to compress a wet steam, it is difficult for a compressor to compress a wet steam. So we have to increase the size of the compressor. So when we increase the size of the compressor, then work input will be more. This is the limitation associated with the 0.4, that is this point. These are the references used in this video. Thanks. Any questions you can write to me gaurav.catm@gmail.com.